This is the video notes for lesson 6 in unit 3, another day. So this is a solidify understanding. It begins with a jump start. And in the jump start, we need to decide which one does not belong by examining each function and determine which one is not like the others. Really, all of them don't belong for different reasons. So let's look at each table, graph, or equation one at a time, and we will think of a reason for each one to not belong. So let's first look at A, which is this table. So what can we tell about this? So this is our A0, our starting value right here. So that's interesting. So our y-intercept is -3. So y-intercept is -3. So that's something that might make it different than the others. Let's see, what's the pattern here? So it looks like we are minusing 2 each time and then adding 1 each time. So it looks like the pattern or slope is -2/1. Okay, so those are things that are unique for this table. Let's look at B. So for B, looks like the y-intercept is right here at 0, -4. So that's something unique about B. It's the only graph of this whole thing, so that's something unique as well. Only graph. And might as well find the slope for this. So the pattern for this looks like it goes up 2 and right 1, so 2/1. So that has a similar slope to the first table in A, but it's positive where the table was negative. Let's look at C. So in C, looks like our y-intercept is right here at +1, so that's our y-intercept. So that's kind of important. That's different than the other two. And then let's look at our slope. Looks like we're adding 2 each time, and we're adding 1 for x. So it looks like m is 2/1. So that is the same as the graph, but has a different y-intercept. All right, let's look at D. So our last one, this is the only one that's an equation. So this is the only equation. And do you see that there's no A0 here or y-intercept? That means that it's actually +0. It's at the origin. So the y-intercept here is actually at 0, 0. So that's unique for the equation. So definitely when you pick out why a table or graph or equation is different, definitely look at the y-intercept and at the slope. Those are great reasons. So I'm just going to say see above for my reasons, and just to write a note, compare y-intercepts and slopes. Okay. Now let's go ahead and move on to our launch. So it looks as if, since this is a solidify understanding, that this lesson is made up of a whole bunch of problems that we need to model using tables or graphs or equations. Those 3, table, a graph, or an equation. So I think the launch is this first problem. It says, every day when Rashid's mother comes home from work, he asks her how her day was, and she says, another day, another dollar. Being a mathematical thinker, Rashid started imagining the function that would model his mother saying. His thinking went like this. On day 0, she hasn't worked, so she has $0. On day 1, she works and gets $1. On day 2, she gets another $1, so she has $2. On day 3, she gets another $1, so she has $3. Rashid visualized this graph of the function. So days versus dollars, and every day she gets one more. So this is what the graph looked like. If we were to model the situation using a table and an explicit equation, it would look something like this. So let's go ahead and build a table and a graph. Sorry, and an equation. So here's our table. We've got f and f of x, which is just y. So on day 0, she's got 0, day 1, 1, day 2, 2, 3, 3. If we were to write the function for this, so f of x equals, it looks like we're adding $1 for every day that goes by. So our slope or pattern is 1/1. That goes with our variable, and our 0 term is 0, because on day 0 she's got 0. So that is the equation for it. If we want to simplify it, we could just write this. We could write f of x just equals x, because the 1/1, 1 times x is just x, and we don't have to write the plus 0. As Rashid pursued this thinking, he wondered what would happen to his function if he started with $5 on day 0 and then earned $1 a day. So now he's switching it up. Instead, he's starting with 5, but has the same amount that he's earning each day. So we need to model this using a table graph and an explicit equation. So let's go ahead and graph what it would look like first. So he starts with $1, $2, $3, $4, $5, right? And he goes up $1 one day, up $1 one day, up $1 one day, up $1 one day. So it goes like that. And I'm not going to graph anything outside of the first quadrant, just because I feel like this is days and money, so we're not going to have negative days and negative money. Okay, let's go ahead and build our table for this. So we have x, and we're going to call this one g of x. So rather than using the same f of x, that we have different names for them. So on day 0, it's already at 5, day 1, 6, day 2, 7, day 3, at 8. Okay, which means the equation for this looks very similar to the one that we just did, except for we're shifted up by $5. So g of x is going to be the same slope 1/1, the same pattern 1/1. So I could write 1/1 x, and then instead of plus 0, it'll be plus 5. You can simplify this and write just g of x is x plus 5. Now, the follow-up question for this is compare the graph in problem 2 to Rashid's original graph. What do you notice? Well, I am definitely noticing that g of x is always going to be bigger than f of x. And the reason is because of that $5 start on day 0. Because $5 on day 0 was added to g of x. Okay, in the end, what did that $5 on day 0 added to g of x do? It shifted g of x up 5 boxes. So g of x is shifted up 5 boxes. Okay. All right. Number 4. Rashid thought about all the bills that his family needed to pay and wondered what the function would be if the situation changed. So that on day 0, they owed $10 and then added $1 a day. All right, so this is definitely going to shift things, but instead of shifting 5 boxes up, it's going to shift 5 boxes down. So let's graph that starting value. So negative $1, 2, 3, 4, 5, 6, 7, 8, 9, 10. but we still gain $1 a day, so we're still going up this way. Okay, so we go like that. Sorry, my line was crooked there at the end. Here, let me try that again. Okay, let's try one more time. Okay, good. So this is, again, days is X and money is Y. Our equation is going to look pretty similar, but instead of plus 5 like we had in G of X, let's call this one H of X. We're going to have the same pattern, 1 over 1, right? 1 day goes by, $1 we gain. But this time we're going to minus 10 because we start with that $10 owed. I can simplify this and just write it as X minus 10. Okay, now we're going to do a comparison of the 3 graphs. Compare the 3 graphs and equations. What do you notice? So this is what we're noticing. We are noticing that G of X is definitely greater than F of X, but F of X is greater than H of X. So, and H of X is now the lowest because it was shifted those 10 boxes down. So I'm going to actually write that note in here. H of X is shifted 10 boxes down. Okay. All right. Number 6. Rashid thought $1 a day is no way to get ahead. What if I start with $1 on day 1 and double my dollars each day? That means I'd have $2 on day 1, $4 on day 2, $8 on day 3, and so forth. I'd come home from work and say, another day, another double. So for this one, I'm actually going to do the table first, and then I'll graph it. So it says, let D of t be the function that models the situation. Represent D of t with a table, a graph, and an equation. So let's start with the table. So we have our table. We have time going by in days. We've got D of t, which is the dollars on any given day. So on day 0, we've got 1. On day 1, we've got 2. On day 2, we've got 4, right? It's doubling. On day 3, we've got 8. On day 4, we've got 16, and so forth. So that is our situation. So when we graph this, let me zoom in a little bit here. So our starting value, day 0, was $1. And then on day 1, we're at $2. Day 2, we're at $4. Day 3, at 8. Okay, so that looks like a curve this time. Okay, so this is going to be a geometric, well, not geometric because it's not just dots. Well, it could be just dots, but I'm going to call it exponential because that was the most recent term that we learned for this type of situation. And then our equation, because it's exponential, is going to be the starting value. So D of t equals 1, and then the pattern, which is 2, and then because it's that curve, that exponential growth, t, the variable, is going to be in the exponent. Okay. And you could also simplify this. You could write D of t equals just 2 to the t power, because anything times 1 is just itself, so we could do that. But we have to know that it started on day 0, it started with $1, so just remember that. Rashid wondered what would happen to this function if he added $3 to every output. What's your prediction? So I'm wondering if every single answer we add 3 to, if that would just shift the whole curve up. So that's going to be my prediction. Will the curve shift 3 boxes up? That is the question. Okay, so let's test it, right? That's what they want us to do next. In 8, it says, try it. Use an equation, a graph on a table to model function that adds 3 to every output. Okay, so I'm gonna again start with my table. So I'm gonna go like this, and I'm going to have my time and then my original d of t, and then I'm gonna actually create a third column, and this is gonna be d of t plus 3, okay, plus that $3. So times 0, we've got 1. Okay, time 1, we've got 2. Time 2 is 4. Time 3 is 8. And day 4 is 16. So now we're going to add 3 each time and then graph it and see what it looks like. So 1 plus 3 is going to be 4. 2 plus 3 is 5. Okay. 4 plus 3 is 7. 8 plus 3 is 11. And then 16 plus 3 is 19. Okay, so let's graph as much of that as possible. So this is what we are graphing. We're graphing right here time, and then when we added 3 each day. So we're ignoring that original middle. We're just graphing those two that I've highlighted in yellow. All right, so at time 0, we've got $4. At time 1, we've got $5. At day 2, we've got 7. At day 3, we're all the way up at 11. 7, 8, 9, 10, 11 is right there. So this looks really, really similar to the one that we just did. But just raise 3 boxes. So I think that our prediction was correct, that how does the graph of d of t compare to the new function d of t plus 3? It is shifted up 3 boxes. Yes. It is shifted up 3 boxes. Okay, cool. If f of x equals x, what do you know about the graph of f of x plus b? Okay. B represents any constant number. All right, so now this is asking us to try to think of, okay, just a generic rule. What if I add something to this linear, right? This is the straight line that goes through the origin that has a slope of 1/1. What if I just add any number? So let's say if I add a positive number. So let's say if b is positive, then the graph moves up that amount. Then the graph moves up b boxes. Okay, but what if b is negative? Then it's going to just move down. So if b is negative, then the graph moves down b boxes. Okay, interesting. Let's see if we can make a rule for, so this was kind of the rule for linear, right? Our observations for linear. Let's see if we can make a rule for exponential, right? This next one, exponential. It says if d of t equals 2 to the t power, that's exponential, that'll be a curve. What do you know about the graph of d of t plus b? B represents any constant number. So I think that it's pretty much the same rule as for linear. So let's write if b is positive, then the graph moves up b boxes, like that amount of boxes. Graph moves up b boxes. And fill in b with whatever number, at least as long as it's positive. If b is negative, then the graph moves down b boxes or b units. Then the graph moves down b boxes. Okay, so those are some really good observations, some good rules for us. So let's see if we can just apply this to any equation. So they give us a graph. It says compare the features of f of x and g of x. So f of x looks like it's 1/2 to the x power plus 1. So it looks like it has a shift of up 1 box from this original. So this was the original curve, right? And then this right here shifts it up a box. Up 1 box. The whole curve. So let's see if we can graph this. And then we'll make some comparison observations. So I'm going to do a little table to help me graph f of x. So let's do x and f of x. So 0, 1, 2, 3, right? Okay, so I'm going to replace x with 0. 1/2 to the 0 power is 1. 1 plus 1 is 2. Okay, and then 1/2 to the first power is 1/2. 1/2 plus 1 is 1.5, so 1.5. Okay, 1/2 squared is a quarter, 1/4. 1/4 plus 1 is 1.25. 1/2 to the third power is 1/8 plus 1, so 1.125. So it looks like it's getting smaller, which is very similar to g of x, right? So let's go ahead and graph 0, 2 right here. And then 1, it's 1.5. So it's just gonna kind of skim right here, right here, right here. I should have probably done some negatives. Here, let me do -1 and -2. Let's add that to our table. When x is -1, 1/2 to the negative first power is 2. 2 plus 1 is 3. And then 1/2 to the negative second power is 4. 4 plus 1 is 5. So that'll give us some of our curve to the left. -1, we're at 3, and -2, we're at 5. So it looks like we're going like this. All right, so let's write our comparisons. So let's write something about f of x. So f of x is basically 1/2 x, but moved up 1 box. So let's write that. So first comparison. F of x is 1/2 to the x power moved up 1 box. Okay. What about g of x? Do you see that 1/2 x should have crossed the y-axis right here? That should have been its y-intercept if we didn't add the 1. So it looks like g of x is 1, 2, 3. 1, 2, 3 boxes lower. So let's make that our second observation. g of x is just 1/2 to the x power moved 3 boxes down. Okay, anything else that we could think of? So they definitely have the same domains, right? Domain for both is all real numbers. So that's just to the left forever, negative infinity, to the right forever, positive infinity, right? Because it doesn't, there's no dots ending the curves. They just go left and right forever. The ranges are different though. So let's write the ranges. So ranges. So for f of x, the range looks like it kind of goes flat here at 1. So it goes from 1 all the way up forever. And then the range for g of x looks like it goes flat here at -3. So -3 and then up forever. Definitely both are decreasing and both are continuous. So those will be our last ones. Both decreasing like forever, so negative infinity to positive infinity, and then there's no gap in the data, no weird jumps or breaks, so they're both continuous. Okay, so I think that's a really good list of comparisons. All right, let's do 13 now. 13 says, compare the features of h of x and m of x. All right, so h of x is graphed, m of x we've got a table for, so that's nice. So why don't we graph m of x? So at -2, we're at 10/9. 10/9 is like 1.1, I think. So -2, like 1.1, like right there. And then at -1, we're at 4/3. -1, 4/3. It's like a little bit, like a third of the way to 2. At 0, we're at 2. 1, we're at 4. Right there. And then 2, we're at 10. All the way up here. So let's go ahead and connect that. So that. And let's make some observations. All right, so first observation. So it looks as if they're both increasing, so we can say that. Both continuous and increasing. Okay, and I'm going to write the interval for increasing. That's just from the left forever to the right forever, negative to positive infinity. It looks like, honestly, like right here in this table, do you see this 0, 3, 9, 27? That is the function 3 to the x power. So like 3 to the x power, and then it looks like we just added a 1, added a 1, added a 1. So I think that we can say that m of x is just 3 to the x power shifted up 1 box. And then we can say that h of x is also just 3 to the x power shifted, looks like it's shifted down how much? I think it's shifted down 2 boxes. Okay, and I'm going to zoom into the graph and check that now. So if 3 to the x power should have crossed here, yeah, so you see that? It's down 2. Okay. Okay, let's think about our domains and our ranges. So looks like m of x and h of x have the same domain. So m of x and h of x have the same domain. Okay, and that's just all x values, negative infinity to positive infinity. And then, but their ranges are different, right? There are different y values. So ranges. So let's say the range for m of x, which was the table, it looks like it starts at 1 and then goes up forever, so like that. But it doesn't actually touch 1, it just kind of skims above 1. And then looks like for h of x, it skims at -2, but doesn't actually touch it. So that's why I'm doing parentheses, not a square bracket there, and then goes up forever. So it looks like that's a good list of observations. We'll finish up by doing our takeaways now. So it looks like our takeaways are about this vertical translations that we've been seeing. That's what it's called when we shift something up or down. It's a vertical, right? Vertical is a line up and down. Vertical translation. Translation just means move. So what are the effects of a vertical translation on the linear parent function, right? The original parent function, f of x equals x. So the effect on the equation. So let's go through each representation. So the equation, we're going to have f of x, instead of just x, it'll be x plus the shift. The graph will still be a straight line, so it'll still be a linear graph, and there will be no change in the slope with the same slope. It'll have a different y-intercept. So instead of through the origin, the y-intercept is going to be 0 and then whatever that shift is. And then depending on what b is, if it's positive, it'll shift up that amount, or negative, it'll shift down. So we'll write that one more time. If b is positive, each point on the graph, so on the function, each point shifts up that amount. And then we'll say we'll have one more, if b is negative, each point shifts down that amount, shifts down that amount. The next part of the takeaways is the effects of a vertical translation on an exponential parent function, like f of x equals 2 to the x power. So for an equation, this is what it would end up looking like. So equation would be 2 to the x power, and then you just add the vertical shift at the end. So the graph will have the same shape with the same difference between matching points, so like with the same pattern. So let's say graph will have same shape and same pattern, timesing pattern. All right, what else can we say? For the y-intercept, it's going to just be shifted up by b, right? So initially it was 0, 1 for 2 to the x power, but we're going to add the b to shift it up. And then we have the same last observation. Each point will be shifted up a positive b amount or a negative b amount, depending on what b is. So each point is shifted up if it's a positive b, or down if it's a negative b. Okay, we're going to add a little bit of notation, vocab, and conventions. So our parent function is the original function. Original function that's experiencing the transformation. So it's being transformed. And then a vertical translation is just shifting the parent function up or down. Shifts the parent function up or down. Okay. So in this lesson, we learned that adding or subtracting a number to a function results in a vertical translation of the graph. In a vertical translation, functions do not change their shape. They're simply shifted up or down. I hope that this video notes was helpful. I wish you good luck on your practice.